announcement. Okay, so let's get started. So we are happy to have the Saebyeok Jeong. He's going to tell us about solving Riemann-Hilbert problem by Yang-Mills.
Okay, thank you, Satoshi, for introduction and for giving me this nice opportunity to introduce new work. So there has been a little bit change of plan. I decided to focus more on the new work rather than the old work that I've done with Nikita. So this is based on an upcoming work with Nikita and Nekrasov, and it's about solving the Riemann-Hilbert problem from supersymmetric gauge theory. So as you will see, the Riemann-Hilbert problem is about a purely classical one. So it's about solving differential equations basically defined on a Riemann surface. And as you may know, the supersymmetric gauge theory is in purely quantum regime. So you can call it a quantum classical duality. Okay, so I have to introduce what Riemann-Hilbert problem is. And I think the best way to introduce this problem is to introduce a certain second-order differential equations called Panabet-6. So this is second-order non-ordinary differential equation I wrote here. It describes the flow of W as a function of time Q. And then, as you see here, it's nonlinear. And each term is time dependent, so it's pretty complicated. And these theta parameters here, theta infinity, theta 0, theta 1, theta q, are just given data, some complex number that defines the equation. So this is pretty complicated equation. And historically, how did it come out? It came out in the classification of the second order nonlinear ordinary differential equation that has certain property, which is called Panabet property. And this Panabet-6 turned out to be the most general one among those second order differential equations with Panabet property. But I will not even mention what Panabet property is. It's about certain behavior of the singularity of the solution W of Q. I'm just saying it's historically how it came out. But why are we interested in this second order differential equation? Because it arises in studying isomonodromic problem defined on the Riemann surface. So I will introduce this context. Okay, so let me start introducing Fuchsian system. The SL2 Fuchsian system defined on the Riemann surface C. Here my C is the puncture Riemann surface, P1 minus n punctures. Z1 to the Zn are positions of punctures. And I define certain matrix valued differential equations on this Riemann surface. d phi over dy equals ay phi. So ay here is 2 by 2 matrix. Phi is a column vector solution. And ay has a singular structure, pole structure at each puncture zi. They have simple poles, and its residue AI is valued than SL2. So this is what I wrote here. And we impose the constraint that the sum of all the AI sums to 0. This is to impose that there's no additional singularity at the infinity of the sphere. Okay, so this is what Fuchsian system is. Now, given a Fuchsian system, we think about a Riemann-Hilbert map. Riemann-Hilbert map is the map which sends this given Fuchsian system to its monodromy data. So what is the monodromy data? It is for a given loop in the Riemann surface C. So an element in pi1c. We analytically continue the solution phi of y along gamma, along this loop. And the solution, because of the punctures, and in more general, because of the genus that the Riemann surface has, the solution doesn't have it converges in certain convergence domain. It doesn't converge everywhere. So we have to analytically continue properly to come back to its original position So this analytically continuous solution phi prime is phi times some matrix, 2 by 2 matrix M gamma. In other words, M gamma is the monodromy along gamma of the solution phi. So this M gamma, this M eats an element in pi 1c gamma and spits out the matrix M gamma, which is valued in SL2. And because I didn't specify the origin of this gamma, I have to divide by the over conjugation of SL2. So this M is valued in this space, which I call monodromy space. It's a homomorphism from the pi 1c to SL2 and mod by the over conjugation SL2. This is the Colley M space. So I repeat, the Riemann-Hilbert map is a map from the space of Fuchsian systems to the monodromy space. And for a given Fuchsian system, we compute the monodromy data, and that defines a map, RH. Any question on this? Okay. So our main example will be the 4-puncture sphere. I just draw some example. So the position of the punctures are at 0, Q, 1, and infinity. As you can see here, 0, Q, and 1, and infinity. Let me pick a reference point at Y0, the origin Y0. And one example of the loop gamma that I wrote here is this loop, the red line. It goes around the puncture at infinity. So, for example, I can analytically continue the solution phi of y along this loop and come back to the original position y0. That's the left-hand side, and there will be a phi of y0 times certain 2 by 2 SO2 valued matrix. Okay, so this exemplifies what I just told you, how we compute the monodromy data, how we define the Riemann-Hilbert map. All right. So what is the Riemann-Hilbert problem? It's about reconstructing a Fuchsian system from a given monodromy data. So it's a reverse procedure. For a given M in the space Colley M, we want to reconstruct the Fuchsian system that defines this monodromy data, okay? And this reconstruction is not unique. That's because, so let's say I rewrite the Fuchsian system, the equation that defines the Fuchsian system again here. And let's say I let AIs, the residue AIs, vary along the position of the poles, Zi. So this is what it means, AI of Z. And I can vary AI with respect to Z in such a way that the monodromy of this Fuchsian system is preserved along these variations of the AI. So schematically, it means under the map Riemann-Hilbert, the image of AI as a function of Z is a constant. It's just constant M. Okay. So these deformations of AI, or the deformations of Fuchsian system, is monodromy preserving. In other words, it is isomonodromic deformations of Fuchsian system. And these deformations can be described by Schrödinger equations. The Schrödinger is the name of mathematician that discovered this. It's given by these differential equations. So, well, the AI over the Zj is given by this expression. Here, the bracket is just a matrix commutator. And when I equals j, we have this expression. You can see when AI satisfies this differential equation, the monodromy is preserved because you can take this D minus A as a certain meromorphic connection defined on the Riemann surface, and you can compensate the variations of AI with some gauge transformation, and then the monodromy will not change because it's gauge transformation. The variation is just the gauge transformation, and you can just directly see that this equation will imply that the monodromy is preserved. Okay. Any questions so far? Good. So now let me specify further. So let me further restrict to the space of Fuchsian system to E, by which I just mean that I fix the eigenvalues of each AI to be theta I and minus theta I. So determinant of SII is minus theta I squared now. And also divide by the overall conjugation of SF2. What's corresponding to this constraint here in the monodromy space is the conjugacy class of monodromy along each puncture is fixed. So if I go back to my main example, here we have 4 loops that goes around each puncture, and this constraint fixes the conjugacy class of this monodromy. Okay, we're reducing the dimension of the spaces. So now we can just do the dimension counting of these spaces, and we recognize the complex dimension of these 2 spaces is just 2 times n minus 3 for n puncture sphere. In particular, we are dealing with 4 puncture sphere as our main example, then the dimension of the space is 2. Okay. Okay, so for the main example, C, the 4 puncture sphere, we have 3 SL2 value matrices. As I just told you, the eigenvalues are fixed. So determinant is minus theta squared. And we fix the gauge that A infinity is the diagonal matrix. And as I just told you, the dimension is 2. We can parameterize the space by certain variable coordinates W and PW, which is defined in the following way. So the 1-2 component of the A, which is 1-2 component of this expression, has 0, and this 0 is defined to be W. And PW is the 1-1 component of this expression valued in W. Y is replaced by just defined W. So this is just certain choice of the coordinate. Maybe it's not very important right now, but the point is that this is certain coordinate system to parameterize this 2-dimensional space. And what's important is that when we write the Schrödinger equation for this 4-puncture sphere Fuchsian system, I rephrase the Schrödinger equation for our main example. And since we parameterized this A0, AQ, A1 using W and PW, these equations will be differential equations in W and PW. Okay, and I can make it into second-order differential equation for W. And that differential equation is pen level 6. This is complicated computation, but it can be done in Mathematica, and it's pen level 6. So this is how pen level 6 arises in studying the isomonodromic problem of Fuchsian system. Okay. Any questions so far?
So far, so good.
All right. If I go too slow or too fast, please tell me. We're gradually getting to the field theory, the supersymmetric field theory, and to do that, I have to introduce a tau function, what is called tau function. first, let me define the Hamiltonian by this expression, trace of AI aj over in zi minus gz. Then we recognize that the Schlesinger equation can be rewritten as a Hamiltonian flow defined by this Hamiltonian. So here, by the way, the bracket is defined by the V+1 bracket written here. If I just compute this explicitly, this bracket AI Hj, I reproduce the Schlesinger equation that I introduced in the previous slide. In other words, the isomonodromic deformations are the flows defined by this Hamiltonian. And then we define the tau function of isomonodromic problem as a common generating function of those Hamiltonian. So it means the HI here is the z derivative of a common function log tau. Okay. So for our case, the four-puncture sphere, we have only one variable q because we fixed the other position of the poles as 0, 1, and infinity. And the statement becomes the Hamiltonian for the panel of 6 is d over dq of the log tau. So we don't have many punctures here, so we only have a single Hamiltonian. We don't have other Hamiltonians, so the meaning of the generating function doesn't mean very much, but still, this is how we define the tau function for the panel of S6. It's an antiderivative for our Hamiltonian. Okay. Now I have to introduce the statement that connects this tau function with the supersymmetric gauge theory. So in any case, we are getting to the supersymmetric gauge theory. So this is the statement. So this conjecture was firstly discussed by Gamayun, Yorgov, and Lisovy. So this is called that's why I call GIR conjecture. The statement is that the panel of 6 tau function that I just described can be expressed in terms of 4D n equals 2 gauge theory partition functions. In particular on the q equals 0. So what is the equation? Equation is this tau of q equals some infinite sum over integers. And what's summed over is the partition function of 4D n equals 2 gauge theory here, z. And this A is the Coulomb moduli of the gauge theory, but it's shifted, integer shifted by this n epsilon 1. M is the masses of hypermultiplets. Epsilon 1 and minus epsilon 1 here are the omega background parameter. And Q is the gauge coupling. So this is not just an arbitrary gauge theory, but it is SU2 gauge theory with the SU2 gauge group, and we have 400 fundamental hyper multiplets. And what you have to note is that this is actually the class S theory defined by the Riemann surface C, which is the fourth puncture sphere. So you have to note that this four-puncture sphere is exactly the Riemann surface that our Fuchsian system was defined. That's associated with this Penlever 6. And I will say why this is not a coincidence. Okay. Oh, and the sum is summed over with the weights exponential n beta. And I will also introduce, I will just briefly introduce what this beta means in the next slide. Okay, so I wrote out the partition function z. So again, tau of q is integer sum. This is a classical part of the gauge theory partition function. This is one part, and this is an instant part. First thing to emphasize is that the right-hand side has some factor of q in front, and it's a series in q. As you may know, the instant partition function of the gauge theory is a q series. And it can be computed in arbitrarily high order in q. It's known how to compute it. If you're familiar with it, for a given order, you can basically write a mathematical code to compute z instant on here. So the left-hand side can also be computed in arbitrary order of q by using this formula. And this is extremely good thing because there has been many studies on the tau function for the Penlever 6 and in the purely mathematical context by Jimbo and Miwa and others, and they were studying this asymptotic behavior around q equals 0. But this formula directly gives arbitrary high order of q. Second thing is that the hypermultiply masses m, I didn't write it here, but in the previous slide, the m, these are hypermultiply masses. They determine the theta parameter that we have seen in the first slide. Okay.
I think it's better to say that the SU2 with NF is equal to 4, right?
Oh, I think I told you, yes.
Oh,
this is the gauge.
Oh, I see. You have written. Okay, sorry. Yeah, thanks.
Okay, let me emphasize once again. This is the gauge, the partition function of the gauge theory with the gauge group SU2 with 4 flavors. In particular, you have to note that this is class S theory defined on the 4-puncture sphere. Okay, for those of you who are not familiar with class S theory, it has for the n equals 2 gauge theory, which has M theory origin. You compactify a stack of M5 branes along this 2-dimensional Riemann surface. And the effective theory along the other 4 direction is the F4 n equals 2 theory that I'm talking about. And the reason why I'm emphasizing this fact is that this Riemann surface, 4-puncture sphere, is exactly where our Fuchsian system is defined that leads to this Penlever 6, okay? And I'm saying that this is not a coincidence. Okay, let me go back to the hypermultiply masses. So what's the mathematical meaning of the hypermultiply masses in the left-hand side in terms of the tau function at Penlever 6? They determine the theta parameters. So m is theta, basically. And what about alpha and beta? So alpha is Coulomb moduli, and beta is certain weights that we are using in the summation. Maybe in this talk, I will not go into very detail, but it's in the paper. But anyway, this alpha and beta parameterizes the 2-dimensional monodromic space called the M, okay? In other words, alpha and beta provide certain coordinate system that parameterize M. I will not write it explicitly in this talk. Okay, and then perhaps what's most important is that you have to note that this partition function of the gauge theory was evaluated as self-dual omega background. So the omega background is a certain supergravity background that allows you to compute gauge theory partition function, because the gauge theory is defined on the non-compact C2. You have to somehow regularize this by introducing supergravity background. So it has two parameters, epsilon1 and epsilon2. But you see that this is epsilon1 comma minus epsilon1, which means epsilon1 and minus epsilon2 are identified. And this is sometimes called self-dual omega background. Okay, so what does it mean? I mean, on the right-hand side, we have some formal sum. I mean, we know how to compute it, but what's the meaning of this infinite sum, and why does the self-dual omega background comes out? I mean, it's not very clear, and that's the main focus of this talk. And at this point, I have to emphasize this conjecture has been proven by Yergov, Lisovy, and Teschner. And they use the AGT correspondence. So the context is that first use the AG correspondence to identify this partition function with Liouville conformal block. Okay, and then we can use powerful tool, the crossing symmetry of the Liouville CFT, whose corresponding operation in the gauge theory side is not very clear, or at least difficult. But the crossing symmetry is very powerful, and then we directly can prove this statement. But I have to emphasize that even in the context of the Liouville CFT, the right-hand side is a formal object. It's a formal sum of infinite numbers of conformal blocks. So maybe it's good thing to physically understand what this object is, what this infinite sum is.
All right, are you going to say what epsilon1 is on the left-hand side?
Oh yeah. So the epsilon1 just plays the role of the mass scale here. So the dependence of epsilon1 is just trivial. So what's relevant is only a over epsilon1 and m over epsilon1. Okay.
Okay.
For example, m over epsilon1 here. So I wrote m here, but it's really m over epsilon1, which are identified these theta parameters. And this alpha here is a over epsilon1. Is it clear?
Yes.
Okay, thanks. Okay. All right. Okay. That's the problem. So we are now really getting to the gauge theory. So to understand this problem, I have to introduce some ingredients in supersymmetric gauge theory, and that's surface defects. So surface defects. We would like to study the 4n equals 2 gauge theory of class S in the presence of certain half-BPS surface defects. So let's forget for a moment about this isomonodromic problem, but let's just focus on the 4n equals 2 gauge theory with surface defects. Okay, I will connect these two stories later. The surface defects I will deal with can be engineered either by OB folding, by which I mean placing our 4n equals 2 gauge theory on C2 with certain OB folding action. Okay, or we can couple certain 2D sigma model to the bulk 4D theory, and thereby generating a surface defect by this. But the point is that in any case, we can exactly compute the partition function of these couples of this gauge theory in the presence of the surface defect on the omega d form C2. Okay. let's take a look one by one. So first, I would briefly discuss how overfolding goes, and then how the coupling to the sigma model goes. All right. First, overfold. Let's consider the Z2 action on C2. It just sends Z1 to minus Z1. It doesn't touch C2. And we consider the overfold defined by this action. And we can map it to the ordinary C2 by just taking Z1 squared. Z1 tilde is Z1 squared, and Z2 is still Z2. Okay. So the gauge theory defined on this overfold can be understood as just a gauge theory defined on an ordinary C2, but by doing this, we allow singularity of the gauge fields along the Z1 equals 0 plane, because this map is singular along Z1 tilde equals 0. And that singular boundary condition along Z1 equals 0 defines surface defect, in particular the Gukov-Witten type. All right, so because of the singular boundary condition, we can choose, the gauge group is broken down to a subgroup that is more or less up to our choice. And here, we're dealing with U2 gauge theory, and the subgroup is chosen to be U1 cross U1 Cartan. All right, so the point is that we want to compute the partition function of the 4D gauge theory in the presence of this Gukov-Witten type surface defect. And this partition function can be computed by first computing the partition function of the ordinary gauge theory, but we only keep the Z2 invariant part. So this is a very convenient way of computing surface defect partition function. And I believe this computation was firstly done by Kano and Tachikawa. Okay. The second way of constructing the surface defect was coupling to 2D sigma model. To do this, we first start from a larger gauge group, which is U2 cross U2. So that's the theory that I drew here. We have U2 cross U2 gauge group, and we have the matter multiplets here and here, and the bifundamental that connects these two gauge nodes. This is n equals 2 Triever, if you're familiar with it. And the plan is to partially Higgs one of the gauge group so that we generate the surface defect. So this partial Higgsing procedure can be understood in the brain picture. The brain picture is very convenient to understand this partial Higgsing. So this gauge theory, U2 cross U2 gauge theory, can be engineered by this brain configuration. We have 3 NS5 brains, vertical, and we have 2 D4 brains suspended between these NS5 brains and infinity. In particular, these 2 finite length D4 brains corresponding to this gauge node. And now what we do by partial Higgsing is that align these two D4 brains across the leftmost NS5 brain. And then what we can do is pull off this NS5 brain into perpendicular direction like this. Then by the brain transition, we generate this D2 brain suspended between NS5 brain and D4 brain. Then you recognize that what's remaining in the 4D bulk is the SU2 gauge theory with 4 flavors. But in addition to that, we have certain coupling to two-dimensional theory coming from this T2 brane. And that's the 2D theory that we are coupled to the 4D bulk. So this procedure tells you how to compute the surface defect partition function of this type. It is, first we compute U2 cross U2 surface, U2 cross U2 gauge theory partition function. And then we, by hand, we impose the Hitchin constraints that allows this aligning. Then we compute the surface defect partition function of this type. Okay. Now, these partition function, so I omit the detail of the computation because it could be very lengthy and it will confuse you more. I will just schematically write the result of the computation here. So the surface defect partition function psi is a function of the Coulomb moduli, the masses of the hypermultiplets, omega deformation parameter, and the gauge coupling, and the complexify Fi parameter of the 2D sigma model. So it looks like this. So it's a sum over Young diagrams Q to the lambda and mu lambda. So this Q is the bulk gauge coupling. Mu lambda is certain measure factor that we impose for each lambda Young diagram. So if we don't have this part, this is just for the gauge theory partition function. But because of the surface defect, we have additional contribution from the 2D surface defect. So it's sum over non-negative integers, and it's weighted by z to the minus k. And this k, x, k, comma lambda is a complicated function of Coulomb parameter, masses, and epsilon 2. And they are coming from the contributions of 2D, 4D coupling. So this is schematic. Yeah.
I have a question. So is the partition function coming from orbit folding and also computed by this 2D, 4D couples? Does it coincide?
No, they don't coincide. So
okay.
They coincide in the sense, so they lie in the different domains of Z.
Mm-hmm.
So Z lies in our four-punctured Riemann surface, Riemann sphere. And there are many convergence domains in that Riemann sphere.
Okay.
So for example, Z can be around 0, Z can be near infinity, or Z can be in between Q and 1.
Yeah.
And these surface defect engineer the surface defect partition function in different domains, basically. And here I'm writing only one of the expression. In particular, D is nearby infinity, so that this expression is convergent.
But my understanding is that if you do orbit folding, so you treat all the puncture equally. Is it true?
Or the punctures equally.
It depends on how you do the ramification, how you introduce ramification, but
are you talking about the higher rank case where we have maximal puncture and minimal puncture?
No. Yes, you do. Okay. Let's discuss later. Okay, that's fine.
Yeah, this is schematic for the 2D 4D couple system partition function. And here I wrote beta because the 2D sigma model has the choice of the vacuum. So this choice of the vacuum is reflected in this beta here. So maybe it's instructive to take some degeneration limit of this partition function to recognize what this object it really is. if I just take the, if I just turn off the bulk gauge coupling, so send Q to 0, send Q to 0, this part just becomes 1, and I just have this contribution. And you will just recognize this is nothing but the vortex partial function, because for the surface defect theory. And for the case at hand, it's actually the vortex partial function for the sigma model, with the target being this local Calabi-Yau, O-1 plus O-1 over P1. This vortex partial function is actually a hypergeometric function. So in other words, this is purely 2D partial function. In other degeneration limit, for example, I can take the complexify F parameter to infinity, then this contribution will just be 1, and I will just recover this part only. It's nothing but the 4D bulk gauge theory partial function. And I just told you that this 4D gauge theory is SU2 gauge theory with the SU2 gauge group and 4 flavors. The class S theory with on the 4-puncture sphere. So when both Q and Z are finite value, then this is certain combination of these two. This is certain partial function of the couple system, 2D 4D couple system. Okay. Now we are interested in the chiral ring elements of this 2D 4D couple system. They are chiral operators from the bulk, and they are also chiral operators from the 2D surface defect theory. And they are not freely generated, but they satisfy certain chiral ring relation. I think this is firstly studied by Gaiotto in the surface defect and resolve 1 paper. And but what we have here is the omega deformation. It's not the theory is not on this flat C2. So this relation uplifts to certain differential equations in coupling constants. Okay, so I will not show the explicit derivation of this differential equation, but I'll just state that we can exactly derive this equation by using certain properties of some good, nice observable in 4D gauge theory called Hughes character. This part is a bit technical, so I just say it and state the result here. The differential equation I'm talking about right now is 0 equals this differential operator annihilating the surface partial function here. As you can see, it's differential operator in Z and Q, which are coupling constants. Epsilon 1 and epsilon 2 are omega background parameters, as I introduced earlier. And moreover, we have these deltas parameters. They are some combinations of hypermultiplied masses. So you can just view it as masses of the hypermultiplieds. To help your understanding, in the Liouville CFT side, if you think about if you're familiar with the AGT correspondence, this psi is a degenerate conformal block. And because it's a degenerate conformal block, it has to satisfy a decoupling equation for the null vector. And this is exactly this equation, null vector decoupling equation. The point is that without using any CFT arguments, without using AGT correspondence, it can be pure. This equation can be purely derived in the gauge theory context using the Hughes characters. Okay. Now, this equation now directly connects our gauge theory to the Penlevet 6 problem. What we do is take epsilon 2 to 0 limit. It's called Nekrasov-Shadashvili limit. And this partition function will show asymptotic behavior like this: epsilon 1 over epsilon 2 S. In other words, this S is like the free energy of the effective theory on the Z2 plane. And then this equation can be rewritten in this form: H plus ds over dq is 0. And if you recall the classical mechanics, this is what is called the Hamilton-Jacobi equation. And in particular, this Hamiltonian is exactly the Penlev-6 Hamiltonian that I described earlier. Okay. So the free energy of the surface defect theory is identified with this Hamilton-Jacobi potential. You have to note that the S is purely quantum object, but it's identified with purely classical object here. So in this sense, it's quantum classical duality. And if you look at this equation more carefully, you may recognize this is something very similar to what we have seen earlier. You take the derivative of S with respect to Q, the time, then you produce Hamiltonian. This is more or less how we define the tau function. The dq derivative of log tau is equal to Hamiltonian. That's how we define the tau function. And this equation tells you this S is more or less the log tau. Okay. All right. But there's a mystery. Before going to the next slide, is there a question? Okay, so far so good. So basically, I have told you two ways of connecting the Penlev-6 problem to the supersymmetric gauge theory. One way is the GIL conjecture. So let me go back a bit. The GIL conjecture tells you the supersymmetric gauge theory is connected to the Penlev-6 problem. And I just have shown you the second way, which is this, the Hamilton-Jacobi equation. So this S is a free energy of the surface defect theory, but it's also the Hamilton-Jacobi equation, Hamilton-Jacobi potential. It satisfies Hamilton-Jacobi equation for the Penlev-6. So there are two ways, but there's a mystery because in the first way, the field theory, the first supersymmetric field theory part was associated. We set the self-dual omega background. Remember, in the infinite sum of the expression of the tau function, we summed the gauge theory partition function in the self-dual omega background. Meanwhile, in the second way, we are dealing with the Nekrasov-Shadashvili limit, where epsilon 2 is going to 0. So what's happening here? We're basically getting the tau function of the Penlev-6 in two different ways. But in the formal way, we have epsilon 1 equals minus epsilon 2. On the other hand, we have epsilon 2 going to 0. So how do we reconcile this? And this is also related to physically explaining the GRI conjecture, because on the second way we know how physically the Hamilton-Jacobi problem for the Penlev-6 arises in the Nekrasov-Shadashvili limit. If we can connect these two stories, if we can explain the first story from the second story, then we can get the physical understanding of the GIR conjecture. So that's what I will explain from now in the remaining 10 minutes. Okay, so the main player is a blow up. What's blow up? The notation is C2 hat, and basically, well, this is some equation, but basically it means replacing the origin of C2 by P1, an exceptional divisor P1. Okay, so this is the picture. And there has been many studies of gauge theory on this blow up C2. And in particular, the n equals 2 gauge theory partition function on this C2 blow up, which I wrote Z hat, is an infinite sum of the product of gauge theory partition functions. But there we have to be careful because of the fluxes along this P1. We have to sum over. We have to shift the Coulomb moduli inside the sum properly, and also we have to shift the omega deformation parameter. I mean, so basically the idea is that the fixed point of the isometry before the blow up it is just a single point at the origin. But after the blow up, the fixed point of the isometry becomes 2 because we have north pole and south pole of the P1. So that's why the right-hand side is given by the product of 2 contributions. One is from the north pole and the other is from the south pole. And locally nearby these fixed points, we experience the isometry action differently. So that's why these epsilon parameters are shifted. Okay. Now, the physics should not depend on the size of the P1. In other words, we can shrink down this P1 to 0 size. And then this left-hand side will just be reduced to the ordinary partial function Z. So Z hat will just become Z. So we get this equation. This equation was firstly suggested and proven by Nakajima and Yoshioka, as you may be familiar with. And it's known that this equation contains rich analytic information on the gauge theory partial function Z. In particular, they studied this asymptotics of gauge theory partial function in the limit of epsilon 1 and epsilon 2 going to 0. And they used this equation to prove that this F, the free energy F, is identified with a Saebyeok-Witten prepotential. So this is very useful. Now, for the application to our story, we need an additional feature, which is surface defect. And the idea is to do the blow up with the surface defect. As you recognize here, this is ordinary C2, and I put the surface defect on the Z2 plane, and I do the blow up. Now, the picture looks like this, and the surface defect is attached to the south pole of the P1, and the north pole doesn't experience the surface defect, okay? And how about the blow formula? The blow formula will become like this. The surface defect partial function, which is the left-hand side, the left part of the picture, is equated with the right part of the picture, which is sum over integers because of the fluxes along P1. And the contribution from the north pole is just Z, the partial function without the surface defect, because as you can see here, this locally around the north pole, you don't see the surface defect. But locally around the south pole, you see the surface defect. So the south pole contribution is psi. So this is new blow formula with the surface defect. This was firstly discovered by Nekrasov. He has given many talks about this. And what we have done in our paper is to confirm this formula in various checks. For example, we can analytically continue this Keller parameter or the complexify Fi parameter to various domains, and this equation has to be consistent with the analytic continuation of psi. but I will not go into detail of this check. For now, I'll just introduce this new flow formula. Now, the idea is that to take the epsilon 2 to 0 limit of this equation, then the result is this. So the point is that because the shift in the epsilon parameters, even though we're taking epsilon 2 to 0 limit, the Nekrasov-Shadishevili limit, for the z part, for the contribution from the North Pole, it's self-dual. Epsilon 2 equals minus epsilon 1. So in that way, we are connecting the epsilon 2 to 0 limit to epsilon 2 to minus epsilon 1 limit. Okay. And so the right-hand side is basically the GIR expression for the tau function, and that's equated with this expression written in terms of the free energy S. I repeat, psi has the symptotic behavior of epsilon 1, epsilon 2, and S. And by using the fact that the S is identified with the Hamilton-Jacobi potential for the pen of S6, we can prove that the log derivative of this tau function is equated with the pen of S6 Hamiltonian. In that way, we drive the GIR conjecture. I omit the detail of the computation, but I just presented the idea, how it goes. So in particular, this infinite sum now has a physical meaning. The right-hand side is not just a formal sum. This sum is coming from the fluxes along the P1. In that sense, this has physical meaning. Not. Okay, so.
Sorry, what is beta? Oh, you're going to talk about, okay.
Yeah, the beta, as you recognize here, so let's focus this part, the weight exponential n part.
Mm-hmm.
This part is beta, right?
Yeah.
So on this slide, I wrote beta equals this.
Okay,
BSO.
okay. I see.
So we identify the mononomial parameters alpha and beta in gauge theory parameters. So alpha is just Coulomb moduli, basically, and beta is, as you just pointed out, ds over d alpha. S is free energy and A is Coulomb moduli. So this is again gauge theory terms. So what this tells you is as a bonus, you may recall that the momentum P is given by ds over dz, the derivative of S with respect to z. And this tells you beta is ds over d alpha. And this implies that S is also the generating function of the Riemann-Hilbert map. This just means that by solving this equation, you can implicitly determine z. That's not. Oh yeah. By solving this equation, we can implicitly determine alpha, and then you plug it back to this equation. Then you determine beta in terms of z and p. So that defines a map from z, p to alpha, beta. So that defines the Riemann-Hilbert map, and moreover, if you define the map in this way, you immediately see that the symplectic structure is preserved. So this is a symplectic morphism, but so basically S is a generating function for the Riemann-Hilbert map. All right, so that's I basically told you everything I wanted to tell you, and of course I didn't show many things because of the time. I didn't show the detail of the derivation. That's in the paper, and also analytic continuation for the below formulas are very interesting as a consistency check, and that's also described in the paper. And how the background transformations from the pen of S6 acts. That's also an interesting part. And I didn't say about this. And also determining the alpha and beta parameter. Exactly, that's done in the paper. So we can think about a few future directions. We can add, for example, more punctures. There will be bigger gauge groups, like SU2 cross SU2 and so on. We can also think about higher ranks. Then the gauge group will be bigger. I mean, the rank of the gauge group will be higher, so SU3 and so on. And there are also interesting features associated with the S duality. In the GIA paper, they also has the expression for the tau function around q equals 1 and q equals infinity. So, well, as you may, we can expect that q equals 0 and q equals 1 regime and q equals infinity regime are connected to each other by S duality transformation in the gauge theory part. So maybe you can say something about these expansions too. And moreover, maybe there could be some application of the new Blow formulas in the presence of the surface defects. All right, so that's everything for my talk, and thank you for your attention.
Thank you very much. Any questions?
Thank you for the talk. I have a little bit of a naive question, I think. When you wrote down your Riemann-Hilbert map from E of theta to M of theta, both of those guys were too complex dimensional. But
oh, yeah.
I thought, so that's fine. But I thought the fibers of that map had some positive dimension because we had these isomonodromic deformations. Is that right?
Yeah, that's correct. So along the isomonodromic flow, they are mapped to the same alpha comma beta. Is
okay,
that what
great.
you mean?
So so the fiber dimension is 1, and the image of the map is a one-dimensional locus inside M of theta.
Yeah, that's what's happening. Yeah, so, along the flow of the Q, Z of Q, and P of Q, they are mapped to the same alpha comma beta.
So there's some particular one-dimensional locus inside M of theta that's cut out, i.e., in terms of your alpha and beta parameters. So does that show up for some reason when you try to write down all these formulas, that one-dimensional locus is privileged in some way?
No, I just looked in this way. We first fix alpha comma beta. So we first fix the monodromy data and see which Fuchsian system will produce this monodromy data. So that's how I view.
Sorry, so unless I'm misunderstanding, for most monodromy data, there should be no Fuchsian system that reproduces that data.
Sorry?
So unless I'm misunderstanding, it seems that for most pairs, alpha and beta, there should be no Fuchsian system that reproduces that data. Because I thought the image of this RH map was a complex one-dimensional locus inside the complex two-dimensional space.
Wait. No. Maybe I didn't explain properly. So this is a symplectic morphism which preserves a symplectic form. So this has to be for given alpha and beta, we have to be able to construct certain C comma P.
I see. So RH is a symplectomorphism, but I thought that it had positive dimensional fibers.
Looks to me just symplectomorphism. I don't know.
I'm happy with the statement that it's a symplectomorphism, but then what happened to the positive dimensional fibers given by isomonodromic deformation?
Maybe it's wrong to say it's a positive dimensional fiber. So right now I'm confused a little bit. No, but
okay, yeah, no worries. Maybe you got rid of the isomonodromic deformation direction somehow when you restricted E of theta. I don't know. Okay, that's fine. I was just trying to clear that up. That's okay. But sorry, go ahead.
We're fixing Q. So it's like we are fixing Q to talk about this map. So if we vary Q, then the map changes. Do you understand?
Oh, I see. I see. So Q is the isomonodromic deformation direction.
For each Q, one Riemann-Hilbert map is defined. So maybe I have to write subscript here, RHQ.
Yeah, sure, that's fine. Okay, I see. That's very helpful.
It's a simple automorphism.
So in particular now, if just to make sure I've got the pieces right, yeah. So go ahead and fix Q. If you want to start with some alpha beta and actually solve your Riemann-Hilbert problem of finding a Fuchsian system with that monodromy data, what exactly do you do in order?
Why exactly do you? So do you mean? Are you asking about the connection to the supersymmetric gauge theory?
Yeah, in either language, either from like the math, whatever, or you know the supersymmetric defect theory partition function.
All right, so let's go from the beginning. So we are given with the monodromy data an element in this m theta, right?
Yeah, sure.
And then it's associated with a Fuchsian system with that given monodromy, which produces that monodromy data.
Right, and the question is how to find it explicitly.
Well, at this point, I'm interested in the tau function that's associated with that system. So.
Yeah, okay. So I understand the statement that the tau function is given by the supersymmetric defect partition function, and you take various limits, and that was all very beautiful, and I liked it. But I just want to know, for the purpose of the original Riemann-Hilbert problem that you motivated your talk with, of explicitly finding the Fuchsian system, how do you do that now?
If you're interested in constructing this map RHQ, then we look at this formula. So P is expressed in terms of ds of dz, and S is a function of alpha and z. So this, by solving this, we implicitly determine alpha as a function of z and p.
Oh, I see. Great. And you can equivalently solve it backwards and get RH inverse.
Yeah, you plug it back to here, then you determine beta as a function of z and p, and that means we're determining this RH at q.
Yeah, so the Riemann-Hilbert problem, as I understood it, was actually solving for RH inverse, but okay, you can also do that. Okay, beautiful. Yeah. Thank you.
Any other questions?
I have a question. Thank you for your talk. I wanted to ask about this 2D 4D coupling. You have shown this formula, but could you give any idea what is it explicitly? In a sense, what is the form of this 2D contribution?
The surface defect contribution. This part.
Yes, this one.
Right. I didn't write how to compute the partition function explicitly, but I just delivered the idea. So let me. So the partition function looks like the bulk contribution times a certain 2D 4D contribution. So it's like it's just in the limit where we turn off the bulk coupling, it goes to the vortex partition function. This just reduces to the 2D partition function. But because the coupling to the bulk, it has some complicated feature.
Is it some of some factorized expressions or not?
By factorial expression, you're referring something like hypergeometry function?
No, I mean a kind of a recursive formula where we have some of a huge number of factorized expressions with numerators and denominators. So
basically, this can be this has such an expression, in terms of just like the recursive partition function, it has such expression. What I have done is I can rewrite that expression. I can divide into 4D bulk contribution and then 2D 4D coupling contribution.
And what's the kind of class of surface defects for which you can do that explicitly?
Oh, I can also do a more complicated thing, like for example, this target of the sigma model is some vector bundle over flag variety, but this is actually the canonical surface defect in first discussed by you and Greg and Gayota. So,
but the class for which you can compute is, say again, so any homogeneous vector bundle or something over a flag variety?
Yes. So all of these surface defect are coming from the overfolding action or the pricing in this way. And if I rearrange this partition function in this form, I recognize which 2D sigma model I'm talking about. And that could be the vector bundle over the flag variety.
Oh, I see. But you're saying it's not known how to do it if someone comes to you with just a kind of random sigma model with G symmetry?
Right. So I'm starting from certain construction of the surface defect, and I rather recognize this contribution has to do with this certain sigma model.
Got it. Thanks.
Yeah.
But
Thank you.
It's the surface that come from M2 brane, not M5 brane.
So here I'm restricting to that specific surface defect that's coming from single insertion of M2 brane.
I see. But what I meant is if you wrap the another M5 brane for M5 brane on the Riemann surface, I mean, you have to treat all the puncture equally, right? So you have to impose all the ramification data to the punctures in that case. You have to overfolding all the punctures.
So in terms of the Microsoft function, do you know how the expression goes?
Yeah.
Okay.
But that's different from different surface defect you're talking about, I guess.
Yeah, it seems so.
And if you do that, the partition function will satisfy, I think, KZ equation instead of this DPZ you have written down.
You're right.
Yeah.
You're right.
And do you understand the relation between them? Because I mean, KZ is just a quantization of Schrödinger equation, right?
Yes. So yes, but here, because we're dealing with the SU2 gauge theory, there's a correspondence between the solutions of KZ and BPZ. The equation actually becomes the same, and
it coincides. Okay.
In higher rank, of course, they have to be distinguished.
Yeah.
For this discussion of KZ BPZ correspondence, I think Nikita has a paper which is coming in very soon.
Okay.
Who has a paper?
Nikita.
Oh. Okay.
Any other questions? Okay, if not, let's thank the speaker again, whatever method.
Thank you.
I will leave the space for informal discussion for like 10 minutes. So if you have more questions, you can ask him. I will switch off the recording.
Right.